In this video, we will learn about the reactions of alcohols and thiols. This will help us with our learning objective for predicting the products of combustion, dehydration, and oxidation of alcohols, and it will also help us with oxidation of thiols. In the last chapter, we talked about how we could do an addition reaction to an alkene. When we do an addition reaction to an alkene, we form a single bond between the carbons, and this molecule we added, the X gets added to one carbon and the Y gets added to a second carbon. If we did an addition reaction where we had an alcohol, well, if we added a water molecule across our alkene, then this followed Markovnikov's rule, and we could identify what alcohol we would get as a product. That was known as hydration. Hydration is when we add a water molecule across a double bond. So, hydration, add water. And so that is alkene plus water equals alcohol. Elimination is the opposite process. In elimination, we take our double bond, and you can see here that it is exactly the opposite figure. So we take our single bond here, and then we form our double bond by taking that off. And so that would be like dehydration. The D up in front here means we like undo it. So dehydration, we undo it. These are inverse reactions, and so they undo each other. It's a nice pattern to remember. Much like our alkenes and alkynes and other hydrocarbons, our alcohols can also undergo combustion. Just like with alkenes and alkynes and other alkanes, our product are carbon dioxide and water, always. So the pattern for combustion is always that you react with O2 gas to form carbon dioxide and water. Then you just need to add coefficients up in front in order to balance out your atom counts. So here's another figure of that hydration reaction and the opposite process for dehydration. If you ever see these double-ended arrows, it means that the reaction can happen both directions. So the reaction is reversible. And so this is going to require like us to follow Markovnikov's rule and Zaitsev's rule for dehydration. So this is going to require an acid catalyst and heat in order to get it going. So you can see here, this is our acid catalyst. And we want to add something, we want to use an acid that's not going to add to a double bond. So don't use like HCl or something that could actually add to the double bond. So here's our elimination reaction. This is going to follow Zaitsev's rule, where we remove the hydrogen from whichever side has, like, well, this one doesn't need to follow Zaitsev's rule because there's only one other carbon next to it that we can remove a hydrogen from. But you can see that we do form a double bond and we remove water as a product. Here, this molecule also has hydrogens over here that we could have used to remove things. You have to remember that even though those hydrogens were not drawn, that they are there. And so since both this carbon and that carbon had two hydrogens, it won't matter which carbon we remove a hydrogen from. In either case, we will form a cyclohexene molecule, and then water is the product. This is where Zaitsev's rule comes in. So we will have to be careful about which hydrogen we remove from. Remember that Markovnikov's rule for addition reactions means that we add the hydrogen to the carbon that had the most hydrogen, in Zaitse's rule, we remove the hydrogen from the carbon that had the least hydrogens. And so we're going to be removing from this blue one because it only had 2 hydrogens, whereas the gold one had 3 hydrogens. So Zaitse's rule says you remove from the fewest. Remove H from C with least H's already. So now we form this double bond, and you can see that that was our major product. 80% of the molecules that really formed for this one, and only 20% were this one. So that's Zaitse's rule. Here's a practice problem for you. Go ahead and pause the video and try to identify the major product formed by this dehydration reaction. Unpause the video when you're ready to check your answer. I'm going to go ahead and draw in the hydrogens from the other carbons so that I can see the count. Alright, so this carbon has 3 hydrogens, and this carbon only has 2 hydrogens. So I'm going to remove an H from here. That's going to form a double bond between that carbon and that carbon. So there's 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6. Oh, that's terrible. I'm going to redo that. 1, 2, 3, 4, 5, 6, 7. Wait, we're through 6? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yeah. 1, 2, 3, 4, 5, 6. Okay, here we go. I'm removing the hydrogen from there. So that's going to be my double bond is between those 2 carbons. And then I have my water as the byproduct. Oxidation is a different type of chemical reaction. In oxidation, we are going to be increasing the number of carbon-oxygen bonds and decreasing the number of carbon-hydrogen bonds. So we'll be counting these as a way of tracking. You might remember from a previous chemistry class that oxidation is the loss of electrons. Oxidation is the loss of electrons, so it might be a little tricky to figure out why increasing the number of carbon-oxygen bonds is a sign that we have oxidized. But it's a sign that we've oxidized because oxygen is going to be stealing electrons from things it's bonded to. So if we look at this carbon here, this carbon currently, if we look at it, it currently has 1 hydrogen and 1 bond to oxygen. After this oxidation reaction, then it has 0 bonds to H and it has 2 bonds to O. So we can see that the number of hydrogen, we have to be careful about saying hydrogen bonds because that sounds like the intermolecular force. So bonds to hydrogen, it has 0 bonds to hydrogen, and this one has 2 bonds to oxygen. This square bracket over the arrow means oxidation. There's different substances that can be used for oxidation, such as KMnO4 or chromium dichromate. Both of these have lots of oxygens. And so that's how you can help identify them as oxidizing agents. Oxidizing agent means that it goes out and helps the oxidation of this other molecule. So oxidizing agents oxidize other molecules. So here's a pattern of our oxidation. If we look at this carbon here, it currently has, it's a primary alcohol because it has one bond to another carbon. It currently has 2 hydrogens and 1 oxygen bond. After it's oxidized, now it has 1 hydrogen and 2 oxygen bonds. This is known as an aldehyde functional group. So after we oxidize a primary alcohol, we form an aldehyde. That's a good pattern to know. Now we can oxidize our aldehyde because we still have a hydrogen here that can be removed. Once we oxidize this, we have this carbon here has 0 bonds to hydrogen, and now it has 3 bonds to O. And so the oxygen counts increase bonds to O, decrease bonds to H. When we look at our secondary alcohol, this secondary alcohol has 1 bond to H and 1 bond to O. After it's oxidized, now it has 0 bonds to H and it has 2 bonds to O. And then it cannot be oxidized further because there's no H to remove. So our ketones stop. So our secondary alcohols will oxidize to ketones, and then ketones cannot oxidize further. Tertiary alcohols have no hydrogens to begin with, and so tertiary alcohols cannot be oxidized at all. Let's do a little practice with matching to the different types of reactions that happen. You can pause the video if you would like to work this out on your own. So this means carboxylic acid. Carboxylic acid is an oxidation reaction. This middle one is combustion. Combustion reactions always form carbon dioxide and water. So this is going to require O2 and heat. Then this one is a dehydration, aka elimination reaction. I'm going to write elimination reaction. And so that's going to require our acid catalyst and heat. This type of oxidation reaction is very important for our metabolism reactions. When we consume alcohol, we are consuming ethanol, which has this chemical structure. And then in the liver, we have enzymes that act as oxidizing agents. And so we have that can go in place. And then we have testing for it here. An alternative reaction that can happen when ethanol is oxidized is they can turn into acetaldehyde and then acetic acid. This is a vinegar. So when these are fermented to produce the ethanol, it's done so in an anaerobic environment. If there is an oxygen leak, then this type of oxidation can happen, and then it will taste really bad. So that's not good. But these type of tests are also used on the field for field tests for breathalyzer type reactions. So in this nozzle here, this tube, it contains the oxidizing agent potassium dichromate, which changes color as the chromium gets reduced. Methanol is toxic because let's look at the oxidation products for methanol. Methanol will oxidize into formaldehyde. Formaldehyde is a preservative, and then that can get oxidized into formic acid. So you don't want formaldehyde in your body. So don't do methanol. Don't drink methanol. That's bad for you. When we do oxidation and reduction of thiols, they do something interesting. Thiols can form bonds to other thiol groups. So you'll see here that you originally had two of these, and now they're joined by this sulfur. This is known as the disulfide. So this sulfur here was originally bonded to a hydrogen, and now it's bonded to an S. And so this sulfur is oxidized because it's forming more bonds to sulfur. And less bonds to H. We have to remember that sulfur and oxygen are in the same group on the periodic table, and so sulfur has properties similar to that of oxygen. So forming more bonds to sulfur is kind of like forming more bonds to oxygen. We can also take these disulfides and get them reduced, which is shown by this H here, into thiols. So this pattern of oxidation reduction can happen between two thiols and a disulfide. When we perm hair or chemically straighten hair, we are breaking disulfide bonds in the proteins in our hair, forming our hair into the desired shape, and then allowing those disulfide bonds to reform in our hair proteins. So this is the real life application for oxidation and reduction of thiols.